On November 5, 2018, Voyager 2 crossed an invisible frontier, 119 astronomical units from the Sun. Nothing flashed, no camera captured a wall, no alarm announced that the spacecraft had entered a different region of space. Instead, the decisive evidence was something that vanished. Voyager 2's plasma science instrument watched the outward solar wind collapse toward zero. More than 16 light hours later, those measurements reached Earth as numbers showing that the spacecraft had passed through the Heliopause in the solar system's southern hemisphere. Voyager 1 had crossed the same boundary 6 years earlier and provided humanity's first evidence of entry into interstellar space. But its plasma instrument was no longer operating. Scientists had to infer key plasma properties from other instruments. Voyager 2 arrived later with the ability to measure the flow directly. That distinction turned the Heliopause from an inferred dividing line into a sampled physical transition. Only 2 spacecraft have ever crossed it. So what did Voyager 2 measure there that Voyager 1 could not? And how did those readings change the picture of the Sun's outer boundary? Both spacecraft crossed the Heliopause, the boundary where the Sun's outward-flowing plasma gives way to the interstellar medium. Voyager 1 arrived first, crossing in August 2012 at about 121.6 astronomical units in the northern hemisphere. Voyager 2 followed in November 2018 at roughly 119 astronomical units in the south. The difference was not the boundary, it was how each spacecraft could measure it. Voyager 1's plasma science instrument had been switched off after its performance deteriorated. That did not leave the mission blind. Its plasma wave instrument measured electron density through oscillations in the surrounding plasma, while cosmic ray and magnetic field instruments supplied evidence that the spacecraft had entered interstellar space. Voyager 2 carried those capabilities too, but its plasma science instrument was still operating. It could directly measure plasma velocity, density, temperature, pressure, and flux. For the first time, scientists could watch the bulk flow of solar plasma disappear during a heliopause crossing, rather than reconstructing the transition from indirect clues. The probes also crossed in different directions, and during different phases of the Sun's 11-year activity cycle. Their contrasting results cannot be attributed to location alone, because the heliopause expands, contracts, and changes over time. The datasets are complementary, not competitive. Voyager 1 proved the frontier had been crossed. Voyager 2 measured how the plasma changed while crossing it. The discovery did not rewrite all physics, but it changed the physical model of the heliopause. To understand that model, we first need to examine what this invisible boundary separates. The Sun is never still. It continuously releases the solar wind, a stream of charged particles that carries the Sun's magnetic field outward through the solar system. That flow creates the heliosphere, a vast region of plasma and magnetism surrounding the planets. But the solar wind does not travel outward unchanged. Far from the Sun, it reaches the termination shock, where it slows abruptly as it begins to encounter pressure from the surrounding interstellar environment. Beyond that point lies the heliosheath, a broad, turbulent region where the weakened solar wind continues moving outward, but much more slowly. At the heliosphere's outer limit is the heliopause. This is not a solid surface. It is the shifting boundary where pressure from solar origin plasma balances pressure from the very local interstellar medium, the nearby mixture of charged particles, neutral atoms, magnetic fields, dust, and cosmic rays surrounding the Sun. On either side, different particle populations dominate, creating an environmental change instruments can measure directly. Crossing the heliopause therefore means entering interstellar plasma. It does not mean reaching empty space. It also does not mean escaping the Sun's gravity or passing beyond the distant Oort cloud, which may extend vastly farther. The popular image of the heliosphere as a perfect bubble is useful but incomplete. The structure is asymmetric, compressed in some regions and stretched in others. Solar activity changes the pressure inside it, so the heliopause can move inward or outward over time. That motion helps explain why Voyager 1 and Voyager 2 crossed at different distances. A better analogy is an invisible, breathing shoreline. The ocean and land remain distinct, but the meeting point shifts with changing conditions. At the heliopause, the competing environments are plasma and magnetic fields rather than water and sand. The boundary has no visible surface, yet crossing it changes the particles, fields, and flows surrounding a spacecraft. Humanity has sampled that transition along only 2 trajectories. To understand how Voyager 2 reached one of them, we have to return to a journey that began 41 years earlier. Voyager 2 began its journey on August 20th, 1977, launched toward a sequence of planets no spacecraft had ever visited in one mission. Its path carried it past Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. It remains the only spacecraft to have flown close to all 4 giant planets, and the only one ever to visit Uranus and Neptune. Those encounters reshaped the mission. Gravity assists accelerated Voyager 2 and bent its trajectory southward relative to the solar system's plane. After Neptune, the spacecraft left the planetary tour behind and entered a new phase, a long passage toward the edge of the heliosphere. Its cameras were switched off, but the fields and particles instruments continued listening to an environment no image could reveal. The mission that had once photographed storms, rings, and moons was now measuring invisible forces, using hardware built when no human-made object had sampled interstellar plasma. Years later, Voyager 2 crossed the termination shock and moved into the heliosheath, where the solar wind had already slowed under pressure from the surrounding interstellar medium. The spacecraft kept traveling through that disturbed region while its electrical power steadily declined. Every instrument still operating had become precious. By 2018, the environment began to change. On August 7th, Voyager 2's instruments recorded a gradual decline in energetic particles that originated inside the heliosphere. At the same time, galactic cosmic rays arriving from beyond the Sun's influence began to increase. Over the following weeks, their intensity rose by about 20%. These changes suggested that Voyager 2 was approaching the heliopause, but they did not provide a countdown. The boundary could move. The spacecraft was crossing at a different location and during a different stage of solar activity than Voyager 1. Scientists could not assume the 2 events would look identical. Then, on November 5th, several instruments registered coordinated changes. Solar origin particles dropped sharply, galactic cosmic rays increased, the magnetic environment shifted. Most decisively, the plasma science instrument saw the outward flow of the solar wind disappear. No one watched the crossing happen in real time. The data traveled for more than 16 hours before reaching the Deep Space Network on Earth. Scientists then reconstructed the event from measurements of plasma, particles, and magnetic fields. After 41 years in space, Voyager 2 had reached a frontier it was never guaranteed to survive long enough to see. And the clearest proof came from an instrument designed before any spacecraft had crossed the heliopause. The solar wind had gone silent. Voyager 2's plasma science instrument did not look for images. It sampled charged particles flowing past the spacecraft and used their motion to calculate bulk properties such as velocity, density, temperature, pressure, and particle flux. In practical terms, it could tell scientists how fast the plasma was moving, how crowded it was, and how much energy it carried. That capability was valuable at a boundary defined by motion rather than appearance. Other instruments could identify changes in fields and particle populations, but this experiment could test whether solar plasma was still flowing outward around Voyager 2. As Voyager 2 approached the heliopause, those measurements began changing well before the final crossing. The spacecraft entered a broad boundary region about 1.5 astronomical units wide, where the solar plasma became slower, hotter, and roughly twice as dense as typical material in the heliosheath. The environment was not behaving like a calm approach to a fixed wall. It was being compressed and disturbed by the interaction between the outward solar wind and the nearby interstellar medium. Closer still, another thinner layer began about 0.06 astronomical units inside the heliopause. Then, on November 5th, the decisive transition unfolded in less than 1 day. The radial flow of the solar wind collapsed. After the crossing, Voyager 2's plasma instrument no longer detected the continuous outward motion that had surrounded the spacecraft since launch. That absence mattered because the solar wind is the defining plasma flow inside the heliosphere. Once it disappeared, the spacecraft was no longer embedded in an environment dominated by material streaming from the sun. There was no explosion, no visible flash, and no collision with a physical surface. The frontier announced itself through a vanishing signal. This channel examines extraordinary space stories by separating direct measurements from dramatic claims, so subscribe for more evidence-led investigations. The result was more direct than inference alone. Voyager 1's other instruments had already shown that it crossed the heliopause, but Voyager 2 measured the bulk plasma flow through the transition itself. Scientists could see the solar wind weaken, compress, heat, and finally cease to dominate the surrounding space. Even so, one trajectory could not reveal exactly how the boundary moved while the spacecraft passed through it. The heliopause can shift with changing solar pressure, and the region around it remains disturbed by the continuing interaction between solar and interstellar plasma. The silence of the solar wind answered where one environment ended. It did not yet reveal what had taken its place. For that, scientists turned to the density and temperature of the plasma beyond the boundary. The solar wind had vanished, but Voyager 2 had not entered emptiness. Another instrument was listening for the faint electrical vibrations of the plasma now surrounding the spacecraft. The plasma wave instrument could estimate electron density from natural oscillations in that charged material. It did not scoop up plasma directly. Instead, it detected characteristic frequencies, much as the pitch of a vibrating string reveals something about the string itself. Voyager 2's functioning plasma science instrument added direct information about the bulk plasma, including its density, temperature, pressure, and motion. Inside the outer heliosphere, the electron density had been roughly 0.002 particles per cubic centimeter. Beyond the Heliopause, Voyager 2's first interstellar measurement was about 0.039 particles per cubic centimeter, with an uncertainty of roughly 15%. That was an increase of nearly 20 times. Even then, the plasma remained extraordinarily sparse by earthly standards. A cubic centimeter of air at sea level contains vastly more particles. Interstellar plasma can therefore be physically hot without being dense, bright, or remotely similar to fire. Voyager 1 had provided a comparable plasma wave measurement of approximately 0.055 particles per cubic centimeter. The two values were not identical, but they supported the same broad conclusion. Just outside the Heliopause, the nearby interstellar plasma was considerably denser than the material inside the outer heliosphere. Because each spacecraft sampled one narrow path, the difference between their values does not imply a contradiction. Local structure, solar pressure, and distance from the boundary can all influence the density recorded at a moment. Voyager 2 also measured something more unexpected. The local interstellar plasma appeared to have a temperature of about 30,000 to 50,000 Kelvin. Models and earlier observations had suggested a lower range, closer to 15,000 to 30,000 Kelvin. The region was warmer than predicted, although still cooler than the heated plasma Voyager 2 had crossed within the heliosheath. The leading interpretation is compression. Solar plasma pushes outward, while interstellar material presses inward, squeezing and heating matter near the boundary on both sides. Yet scientists still do not fully understand how that compression develops, how evenly it is distributed, or how much it changes as the heliopause moves. What replaced the solar wind was therefore not a calm, untouched interstellar environment. Voyager 2 had entered denser, warmer plasma, already disturbed by its contact with the heliosphere. Density and temperature proved that the spacecraft was immersed in different material. But another measurement created a deeper puzzle. If Voyager 2 had crossed from the Sun's domain into interstellar space, why did the magnetic field seem to keep almost the same direction? The density jump showed that Voyager 2 had entered a different plasma. The particle instruments then revealed how sharply the surrounding environment changed. On November 5, 2018, low-energy ions originating inside the heliosphere dropped abruptly. At nearly the same time, galactic cosmic rays arriving from beyond the Sun's influence increased. These coordinated changes marked a transition between two particle populations, but the boundary was not behaving like a perfectly sealed divide. Before reaching the Heliopause, Voyager 2 passed through a magnetic barrier. The field became stronger there, and that barrier influenced how easily cosmic rays could enter from outside. The Heliopause therefore acted as a real shield, but not an absolute one. The most surprising result came from the magnetic field's direction. Scientists expected that crossing from solar plasma into interstellar plasma might produce a clear rotation. Instead, the field changed by only a few degrees, if it changed at all. Voyager 1 had recorded a similarly small directional shift 6 years earlier. Voyager 2's measurement confirmed that the earlier result was not simply a local accident or an instrumental illusion. One leading explanation is that the interstellar magnetic field bends and drapes around the heliosphere. Near the boundary, that geometry may align it with the solar field on the inside. The exact structure remains uncertain, but the two crossings showed that the magnetic transition can be far smoother than simple diagrams suggest. The particle data revealed another complication. Just outside the Heliopause, Voyager 2 entered a boundary layer where low-energy particles from the heliosphere were still streaming outward. Galactic cosmic rays had also reached only about 90% of the intensity measured farther into interstellar space. The spacecraft had crossed the Heliopause, yet the Sun's influence had not vanished instantly. Voyager 2's crossing appeared more porous than Voyager 1's. Its path passed nearer the heliosphere's flank, while Voyager 1 crossed closer to the front. That difference may matter, although solar activity, boundary motion, and changing conditions over time could also explain part of the contrast. Porous does not mean ineffective. The heliopause still separates dominant plasma populations and regulates cosmic ray entry. But particles can cross, magnetic fields remain connected, and the surrounding region stays disturbed. Voyager 2 did not reveal a broken wall. It revealed that there had never been a simple wall at all. The heliopause is a thin, dynamic transition system where solar and galactic environments meet, compress, align, and leak into one another. It was humanity's second directly recorded magnetic crossing. That measured complexity is more remarkable than the exaggerated claims often attached to Voyager's journey. The measured complexity is more remarkable than the myths attached to Voyager's journey. Voyager 2 did not cross a boundary Voyager 1 missed. Both spacecraft crossed the heliopause, first Voyager 1 in 2012 and then Voyager 2 in 2018. What made the second crossing unique was the working plasma science instrument, not a different frontier. Neither spacecraft has escaped the Sun's gravitational system. In heliophysics, both operate in interstellar space because they are outside the heliosphere, but the solar system extends much farther. The Oort cloud may reach tens of thousands of astronomical units beyond them. Interstellar space is not empty. It contains thin plasma, neutral atoms, dust, magnetic fields, and cosmic rays. Voyager 2 did not strike a visible wall, enter a portal, reverse direction, encounter aliens, or detect an impossible force. Its instruments recorded changes in particles, plasma, and magnetic fields. The claim that its measurements changed physics forever is also too broad. They did not overturn established physical laws. They changed the constraints scientists use to model the heliopause and the nearby interstellar medium. That distinction matters. Unexpected does not mean impossible. The warmer plasma, density increase, particle leakage, and small magnetic field rotation were surprising because simpler models did not fully predict them. Yet each result can be investigated through known plasma and magnetic field physics. The two Voyager crossings also produced different details. That does not mean one spacecraft was wrong. They crossed in different regions, years apart, under different solar conditions. The heliopause moves and changes, so variation is expected. Voyager 2's findings were strong enough to support 5 peer-reviewed Nature astronomy papers. Even so, the spacecraft remains inside a perturbed region near the heliopause, not necessarily fully undisturbed interstellar space. Scientists still debate the heliosphere's global shape and the causes of several local measurements. Removing exaggeration does not weaken the story. It reveals something rarer, a direct test of plasma physics at a boundary humanity has sampled only twice. No third spacecraft is currently approaching an imminent crossing. That leaves a larger question. Why should anyone on Earth care about an invisible frontier more than 100 times farther from the Sun than Earth is? The heliopause matters because it is not merely a distant boundary. It helps regulate what reaches the planetary system from the galaxy beyond. Galactic cosmic rays are high-energy particles moving through interstellar space. The heliosphere cannot block all of them, but its magnetic fields and changing plasma conditions influence how many lower-energy cosmic rays penetrate inward. Voyager 2's measurements showed that the magnetic barrier near the heliopause affects that entry, while particle leakage proves the boundary is not perfectly sealed. Understanding that balance helps scientists model the radiation environment surrounding planets and spacecraft. The second consequence reaches beyond our Sun. Every star with a wind interacts with the interstellar medium around it, creating an astrosphere. Because the Sun is close enough to study directly, the heliopause becomes a laboratory for understanding how stellar winds, magnetic fields, and galactic material meet around other stars. But 2 Voyager trajectories cannot reveal the heliosphere's complete shape. They are narrow cuts through a structure that surrounds the entire planetary system. The third consequence concerns future exploration. Any probe traveling deeper into interstellar space must cross regions whose density, temperature, pressure, and magnetic structure affect both its instruments and the interpretation of its data. Voyager 2 supplied measurements future missions can use, but broader observations and new trajectories will be needed to build a global picture. That opportunity is becoming more limited. In September 2024, engineers shut down Voyager 2's plasma science instrument to conserve the spacecraft's declining electrical power. The experiment that made the unique crossing measurements cannot repeat them. Yet, the remaining Voyager instruments continue returning valuable data from hardware operating far beyond its planned lifetime. The instruments are fading, but the frontier they revealed is still changing how scientists understand the sun's place in the galaxy and humanity's future path beyond it. Voyager 1 crossed the Heliopause in 2012, moving northward at about 121.6 astronomical units from the sun. 6 years later, Voyager 2 crossed southward at roughly 119. They reached the same frontier under different conditions, carrying instrument suites that complemented rather than replaced one another. Neither spacecraft could see the boundary. Neither had been built with certainty that it would remain alive long enough to reach it. Both launched in 1977 for planetary encounters, yet nearly half a century later, they were transmitting measurements from beyond the heliosphere. Voyager 1 established that a human-made machine could enter interstellar plasma. Its remaining instruments detected the particle, density, and magnetic changes that marked the crossing. Voyager 2 then added what its twin could no longer measure directly: the plasma's bulk flow, temperature, pressure, density, and motion through the transition. That was Voyager 2's unique achievement. It did not discover a different frontier. It turned one point on a theoretical map into a measured physical environment. The two paths also revealed that the heliopause is not identical everywhere. But two narrow trajectories cannot define a boundary surrounding the entire sun, and both spacecraft remain within a region shaped by the interaction between solar and interstellar material. Voyager 2 did not make Voyager 1 obsolete. It completed a scientific sentence Voyager 1 had begun. Voyager 2 crossed the same heliopause as Voyager 1, but with a functioning plasma science instrument that directly watched the solar wind disappear. Beyond the boundary, it measured denser, warmer interstellar plasma than many models expected. Its particle and magnetic data also showed that the heliopause is not a sealed wall. Solar particles can leak outward, cosmic rays are modulated, and the magnetic field remains aligned across the transition. What remains unknown is how well two narrow crossings represent the heliosphere as a whole. Which result matters more to you, the direct plasma measurement or the porous magnetic boundary? Subscribe for more evidence-based documentaries about the universe's most extraordinary frontiers.